Okay, well, let's finish this. So I'm going to wrap up with some subsystem code discussion and some fault tolerance, wading into fault tolerance. Nothing super involved. So I began the subsystem code discussion a little bit last time, trying to talk about what all can be sent, what kind of information can be sent in the Shannon paradigm. And we covered like quantum codes, which are corners of the Hilbert space, classical codes where if you kill the coherences, you basically remaining pieces allow you to send classical information. Hybrids, and then subsystems are the ones where you take some of your logical qubits and you assign them as gauge qubits, meaning qubits that you don't use for logical storage, but you are free to manipulate as you wish. So a subsystem code that we can easily study is the one that arises from the 422 code. And that one, the 422 code, just to remind you, is a slight extension of the 412 code. So it has two logical qubits, and its stabilizers are all X and all Z. And its logical code words are here. So the first two are the ones that we already know very well from the 412 code, and then the second two are these additional ones. Turns out that you can fit them. Yeah, I think I mentioned this in the CSS construction. So logical Pauli representatives, there's many different kinds, but here are ones that you can pick, and you can see that they anti-commute as they should. And then what we can do is just not use the second qubit for storage, but as this kind of gauge degree of freedom. And then we get the 4112 code, because one logical, one gauge. But to generally define subsystem codes, you will need basically to define the underlying stabilizer code, and then to define a group to define which qubits you've picked to be gauge qubits. And for that, you can use another group to do that. That's called the gauge group. So this is the kind of nesting that's pertinent to gauge qubits, to gauge codes, subsystem codes. The gauge group here is a subgroup of the normalizer, which is every Pauli that leaves the code space invariant, so which means that doesn't take you out of the code space. It can do a logical, but it doesn't take you out. So this gauge group can be a subgroup of the normalizer, which is basically the entire logical Pauli group and the stabilizer group. And it will include the stabilizer. There's a slight subtlety, is that now it includes the stabilizer and phases. So with gauge codes, you're implicitly free to pick phases. Basically, the stabilizers you can pick can have plus and minus ones added to them as you wish, while still maintaining the same gauge group. So the two extreme cases are if G is just the stabilizer group and the phases itself, then no qubits are gauge. So you've picked 0 qubits to be gauge qubits, and you just have the original stabilizer code. On the other hand, if you've picked G to be the normalizer, the entire logical Pauli group, and also the stabilizer group, then you've picked all the qubits to be gauge, and there are no logical qubits left. We already covered the word gauging before in the context of topological codes. That kind of gauging of symmetries and gauging of global symmetries to become local symmetries is not the same as this gauging, where not this kind of use of the word gauge. Here I'm using it as an adjective. Over there I was using it as a verb, and the definitions are very different. So this is just a warning saying that two kinds of gauging, two kinds of uses of the word gauge are very different. Okay. So subsystem codes have some advantages. One of the early advantages that people noticed was that, well, now you have your gauge group, and the stabilizer group is a subgroup of it, and sometimes you can cook up codes where the gauge operators can multiply to give you stabilizer operators. For example, here, the um, two of these gauge operators can multiply to get you the stabilizer, all x, and um, this means that you can measure the gauge checks, the gauge operators, to obtain the stabilizers. And they're lower weight, which means there's less fault tolerance overhead, and you could, in principle, maybe make this fault tolerant. This is especially true if the stabilizers are large weight. So subsystem codes have there's interesting types of subsystem codes where the gauge checks are order 1 weight as n, the number of qubits increases, so they stay constant, and the stabilizer checks grow. The stabilizer group elements that you would need to check grow. So there you pretty much have to use the gauge operators to really measure things. Another thing is that this idea that you have these kinds of codes where you've assigned some of the qubits to be gauge and initialize them in like a plus, minus, x, y, z eigenstates, you have this kind of picture actually allows you to interpret and collect many different procedures that are the dynamical procedures, including lattice surgery, measurement-based quantum computation, and code switching. And this is discussed in detail in the Boulder lecture that I mentioned at the beginning, all the way in the beginning of my lecture. So let's see, sorry. So the other thing, as I mentioned, that there's these interesting examples of what some people call topological subsystem codes, where the gauge checks that where the gauge group is presented by local, by low weight gauge generators, meaning that a Hamiltonian can be constructed. But the stabilizer group is not presented locally, which means it may not consist of a set of generators that are that are all low weight. So this is a little bit different than just taking a stabilizer code and assigning some qubits to its gauge to be used as gauge, because there you have to start with a stabilizer code that has non-high weight stabilizers. People typically don't study that. So this is different than writing. So you would not be able to write a stabilizer-based Hamiltonian for this, where the stabilizer generators are local. So this actually allows you to realize more phases of matter. And there's some papers and some entries in the zoo about that. The other thing is a trajectory that's been studied for quite a while. Maybe some of you are not familiar with it, but this kind of idea of using two local Hamiltonians can actually be used for error suppression in adiabatic quantum computation. So there, they want to use this few locality once they need to have it be as small as possible, and they want to have some kind of suppression or mitigation. And there's been a direction developing codes for that. This is another slide from the Boulder lectures where I go through some of these things in detail. So there's basically different types of procedures that you can do with gauge codes. The first one is called gauging out. So this is different than gauging. Can't believe that I have to say this, but this is different than gauging symmetries that I mentioned before. Here, you start with a stabilizer code, and you obtain a gauge, a subsystem code. Should probably put subsystem here. There's also gauge fixing, where you change the states of the gauge qubits that you use. And so you go from a gauge to a subsystem code. And then there's something that I call code switching, but maybe I should call it stabilizer code switching, where you go between stabilizer codes by starting with a state that's in a stabilizer code, then picking another stabilizer group F, and then measuring the checks in F, and then the resulting stabilizer group that stabilizes the code will be this kind of normalizer, which is everything in the union of S and F computes with F. So you can salvage any checks in S that commute with F after you measure F, naturally. Because if the check in S doesn't commute with something in F, then that's going to muddle up the measurement because you just measured F. And this kind of idea can be applied in condensed matter settings, and this is basically the idea underlying the Floquet formalism. So Floquet formalism, you're basically doing this in a dynamical fashion. You're measuring different Fs, F1, F2, F3, F4, and you're getting this kind of cyclic family of different stabilizer groups. So yeah, I covered that as well in the Boulder lectures. I do want to mention maybe a little bit more of a technical slide, but there are some subtleties when it comes with gauge and subsystem codes that I maybe mention so that you don't have to run into them later on. As I alluded to before, the you define a subsystem code not just by the gauge group, but by what you pick for the stabilizer group. And the stabilizer group has freedom because now the stabilizer group and the group generated by the I are all subgroups of the gauge group, and you're allowed to pick any commuting subgroup of the gauge group. So you can pick the stabilizer group with different signs. For example, here I've listed the 4 different combinations of signs that you can put for the 422 code. Right, and all your favorite, naive guesses of how to handle stabilizer generator matrices and stabilizer formalism does not account for signs. You have to actually, the sign in these numerical techniques is actually a little extra thing you got to carry around for each stabilizer, mind you. See, for each check. And these signs need to be defined to specify exactly which subsystem code you mean. And then Floquet formalism, when you code switch from one to the other, these signs get randomly assigned. So you have to keep track of them. This is something we learned a bit the hard way. C-not gates are, as is maybe well established by and known, transversal for CSS codes, but only for the +1 eigenspace. There's a compensating pally involved if you actually pick different signs. Little known fact. Similarly, if you look at other transversal gates like these codes all these different definitions that are around for codes that have transversal T gates, those also very subtly depend on signs. And as I mentioned, when you do this kind of code switching, the signs will be random because you're doing a measurement and you have to keep track of them. Okay. So that's the subsystem section. It's very brief because the Boulder lecture notes take care of it in more detail. Now, before going to fault tolerance, we'll cover a little bit of basic error correction. So maybe stuff I should have done in the beginning, but stuff that would be a lot richer now, given that you have a lot more prep after these other 3 lectures. So here's the 412 code. And I want to mention to you the conditions, a very basic and easy and ubiquitous set of conditions called the Null-Flam conditions that allow you to check whether a given code has errors or not. So for stabilizer codes, this isn't necessarily that useful per se because stabilizer codes have more efficient ways to check what's an error by just looking at whether errors anti-commute with the stabilizer group or not. But if you have a code that's more abstract, that doesn't have a set of nice syndromes, like these generalizations of stabilizer codes I mentioned, then there you may have to use the subspace itself and check whether the subspace can in principle detect and correct errors. These conditions don't tell you whether you how to correct these errors, but they just tell you in principle that you can. So one way to kind of make progress in error correction is to cook up a code in some exotic system that people don't expect to have a code, and the way you check that code is to use these conditions. So how do you do it? Well, errors will be detectable if and only if they act trivially on the code words. So one way to think about it is in terms of an environment. I already mentioned in the beginning that there's an environment for diagonal errors, which are these that may affect code words in a different way without transitioning them between each other. You can think of these as potentials that are imposed by some environment that's malicious, that wants to distinguish the code words and therefore sniff out whether you're more in 0 or more in 1. And it can do that by measuring expectation values like this. Then the expectation values, if they're not equal, then the environment will know that you're slightly prejudiced to one or the other, depending on the maximum, the absolute value. And the error will be slightly, at least somewhat detectable. So in order to have the error not be detectable, you have to have the expectation values the same. The other condition is the off-diagonal condition, where you have errors that connect the two code words. And if that happens, then you've basically implemented a logical operation, and you didn't know you did. Somebody implemented a logical operation because the information never left the code space. So in that case, you have to, in order for those errors to be detectable, they better not be implementing any logical operations. So those elements just identically should be 0. And if you write the code words in terms of a projection like this, then there's a succinct way to write this thing, namely that you have this projection of the error PEP equal to a constant times P. So this constant is basically the expectation value of the EJ in the 0 and the 1 state. And this constant need not be 0. Okay, so for example, your stabilizers will satisfy this condition with a constant that's +1, as I write here. The errors, now, what about correctable? Well, so now we have to worry about whether there's two errors mapping into the same error space or not. So if they map you to different error spaces, then two errors are correctable because you can just separately correct them if they're additionally detectable. But if they're mapping into the same error space, then you have to do extra calculation. So if they map you to the same error space, they're correctable if they're detectable and if they undo each other. So the concise way to phrase that is this. And here you can think of these EP pieces as pieces of as like error spaces themselves, because it's like an error has acted on this projection and changed the kets to these error states. And you're looking at how that error space, the kth error space, overlaps with the jth error space, where now you have EJP, where the kets are changed to the error words, but now you flipped it around, so those are the bras. So this is basically a set of overlaps between two error spaces. And those overlaps have to be kind of exactly fit perfectly, meaning that the 0 error state and the 1 error state of the two respective error spaces shouldn't overlap. The 0 states should be on top of each other in the same way as the 1 states, and there'll be a constant at determining that overlap. It need not be 1, so need not be orthonormal. The errors need not be unitary. So, you can have whatever constant you want here. And this kind of is the Schrodinger picture version of what I meant by undo each other, namely that you can basically use like a unitary recovery that recovers against one error to also recover against the other, which means that if it's two errors mapping to the same error space, you can use the recovery for either one, and that'll work. So let's see, and we already mentioned that single qubit bit flips were not correctable for the 4-qubit code because they cannot undo each other. Because when you try to undo, so in this case, the errors are unitary, and so you just use the error itself to undo, and the first error, undoing the first error by itself, is equivalent to undoing the second error, but also implementing a logical, because the error words were not matched up. And you can demonstrate that by calculating by hand the Nilaflam condition, with your two errors, E1, E2 being this first and second qubit bit flip. And if you try to use basically, so another way to phrase this orthogonality is using the E1 error to kind of undo the E2 error, contingent on the normalization, like without caring about the normalization. So when you multiply the two errors, you get this XXII, which is exactly the logical, and because it's a logical X, it'll connect 0 and 1, so the Nilaflam conditions will be violated. Okay, so this is kind of a nitty-gritty thing because when you have an explosion of errors combinatorially like you do with qubits, you have to check this thing exponentially many times, 4 to the n, roughly. It's kind of a pain, and there's several papers trying to look at codes that are not stabilizer, but that have some kind of structure that allow you to do this more efficiently, because it's important. There's another way to kind of view these error correction conditions, not as kind of just some nitty-gritty checks that are many, many different checks, but like as a whole, through what's called the complementary channel. And here you go in a little bit of like open quantum systems, quantum channel theory, where hopefully you will recall that any channel n, in this case we're talking about the noise channel, can be thought of as the action of some kind of unitary on a larger system and environment, and followed by a tracing out of the environment. So this is called a Stein-Spring dilation. It's dilation because this is non-unitary, but this winds up being unitary. And when you write this kind of thing out, you'll basically naturally obtain the Krauss representation of the channel. Now, so this is basically that this is a way of viewing what you see from a channel that has been initiated by this kind of malicious environment. The complementary channel is defined as the opposite. It is defined as what the environment sees. And because it's defined essentially that way, you can look at that channel and see which expectation values and what information from the code space has the environment has obtained. Complementary channel is defined as taking that same unitary, applying it to the system environment state. I have it written as an isometry here with just acting on the system, so the environment state is kind of baked into this U, but never mind that. Taking this kind of unitary action, unitary piece, and tracing out the system instead of the environment. When you trace out the system, you get another channel. That's a channel in the environment, and when you write the unitary in the natural way you would write it here, you actually get this form for this channel. And what's interesting is that immediately you see that the Nilaflam conditions are present in this coefficient next to this state. So the environment will see a state whose dimension is the number of Krauss operators of this channel. Okay? And so it'll see a matrix that's like, m by m, where m is the number of Krauss operators, and the coefficients will be this. And you notice that if my rho L is a logical state, as I've suggestively labeled it, then I can stick in a projection P to the left and to the right of rho L, because it's a logical state, so it always has support only on the code space, which is supported on the projection P. And I can move this P that's on the right all the way to the left by cyclicity of the trace, and you see that that actually recovers the Nilaflam conditions P, N, and P. So if the Nilaflam conditions are satisfied, all the environment's going to see is basically a matrix of constants that only depend on the errors and do not depend on rho. Because this P, N, and P will just become a constant, and it'll stick, you can kick it out of the trace. So there's a very deep connection here that I think is actually a much easier way to explain Nilaflam conditions. And very early on, basically this was noticed and related to some information theoretic relations that you can use, entropies and things that you can calculate that tell you how much the environment is able to obtain from the code without explicitly calculating the Nilaflam conditions per se. And there was a series of papers kind of spearheaded by Cedric Benny and Agnana Reshkov, who cooked up relatively simple computational tools to extract how well you can protect information using the fidelity of this state. So there's entropic quantities and there's fidelities that you can use on the complementary side. Because here you're dealing with a number of Krauss operators, which is not quite the same as here. The dimension here is the dimension here can be, in some cases, smaller. In some cases, it's easier because you can ignore some of these terms because they're small. Right, and this kind of wades us into territory which deals with approximate error correction. So far what we've dealt with is something that is codes that have a distance, which means we impose some kind of an ordering on our errors in terms of severity. Our low weight errors are small, or high weight errors are large. The distance is some number such that any errors below that are guaranteed to be detectable. Right, so everything, the Nilaflam conditions are perfectly satisfied up to the distance, and then no promises. There's going to be some violation by definition, and it could be huge. And it is in stabilizer codes because there's a logical sitting there just above the distance, or sorry, just at the distance. So those kind of like Hamming type codes protect perfectly against some set of errors that's small in whatever metric you pick, and then have some violations. On the other hand, approximate error correction, the codes will never correct anything exactly, but the Nilaflam violations, the violations of the Nilaflam conditions are small. They're smaller. They're say like bounded by some epsilon, and you can stick in this epsilon. What do you mean by small? You can define small in different ways. So you can define it as like some kind of differences between matrices. This is the matrix of the Nilaflam conditions, and then this is just the constant piece of it. And these two should be equal, so this should be 0 if you have perfect satisfaction. If you don't, then these will not be equal, and so there's some kind of maybe absolute value you should take here and bound that element-wise by some epsilon. Also, you can just do your best, try to recover, and take the fidelity, some kind of fidelity between the two states, a recovered state, and using some recovery that you have, some decoder, and the initial state, and see how well you recovered. And that could give you a notion of approximate. And there's a canonical map that is very interesting that does this kind of approximate error correction for general codes and general errors. All it needs is a code and an error to be defined. And that's called the Petz or the transpose recovery. And this is how it's defined. So you need a noise channel E and an error sigma, and a code state sigma to define the Petz map. You can use any sigma you want, but to not prejudice over specific sigma, people just use the code projector P here. And this is what you basically do. Inverses here are defined whenever there's non-zero eigenvalues. So you don't invert it if there's zeros. You see there's some kind of normalizing by the error state. And then you apply the Krauss operator for the Pets map is the adjoint, includes the adjoint of the noise. So you're kind of undoing the noise. And this is exactly true if this Pets map is applied to E of sigma. So if given whatever state sigma you pick for this recovery, if you then first start with that same state sigma here for rho, apply the noise, and then apply the recovery, you'll actually exactly undo the noise. Maybe for those of you who haven't seen this might be surprising. So do speak up if you're confused, but I want to say that this only occurs for sigma. No other state can have this, so you don't have perfect time reversal of non-unitary operations. It's only sigma that you stick into the Pets map that this works for. But what's another magical fact about this map is that it's nearly optimal. So there's a notion of, there's a particular fidelity which called the entanglement fidelity, which for which there exists an optimal recovery that you can find computationally pretty simply. And comparing to that, you can show that the Pets map is actually pretty close to that kind of optimal recovery. And you don't have to compute it. I mean, you don't have to determine it. It's defined for you already. You just have to calculate these inverses and such. So it's computationally a lot easier than finding the optimal recovery, and it's not that far off. Moreover, people in kind of holography areas of QEC have used this fact to have used this third fact to bound this infidelity using entropic quantities that might be easier to calculate, kind of alluding to what I mentioned in the previous slide. So there's relations between this fidelity and some kind of entropy. There was a more recent paper showing that it's actually related to the topological entanglement entropy. And people do often use this kind of Pets recovery map as recovering for recovering a local patch of some many-body system under which has undergone some kind of error on that patch. I guess I want to mention another relatively recent paper which studied, maybe this should have been in the encoding slide, but there's studied relations between the error correcting power of a code, including approximate codes, and the complexity of their encoding circuit. So the complexity is basically related to this kind of overhead you need to implement the circuit, namely the depth of the circuit, which gates you use at the locality structure, etc. So there's a whole kind of area of approximate codes which people study, and I guess I want to mention another strength of approximate codes is that because they're not required to satisfy the Nilles-Flamm conditions exactly for any kind of error, there's actually they can actually circumvent certain bounds that you have for codes that are required to satisfy that. And so there's codes approaching what's called the singleton bound that are approximate, that can approach that bound, but that people are not aware of any kind of Hamming-based, exact error correcting code to approach.
Yeah. So Victor, can I ask a question? Sure. Like, I mean, one of the nice things about, for example, the approximate codes is that they are channel adapted. So let's say you can, given a noise channel, I mean, you can try to optimize for the encoding map and decoding map, both of which are SDPs, using which by running Seesaw, you can find, the strategy. And I mean, and that kind of systematically helps you find these codes, which many people are using for numerics and so on and all. But I mean, I was kind of wondering, if it has been extended, let's say, or studied, I mean, again, they are like, again, subspace codes. Let's say if I want to have some subsystem structure, and your Nilles-Flamm condition will have some, like tensor, G, like there's extra terms that you will get, which you would want to approximately satisfy. So
Right.
some optimization framework where, like I want to say, this is the number of gauge qubits I want, this is the weight of the check measurements I want. And given these constraints, like how do I construct, let's say, some approximate, I mean, I don't know if people have studied anything related to that.
I'm not aware of it. Sounds like it might be useful to check if you can plug those in. So what Kishore is talking about is this computational way of obtaining this entanglement fidelity. So entanglement fidelity is basically you take a Bell state, you encode half of it, one of the qubits in the code, and you send that through the channel, and then you look at the fidelity of the final hopefully entangled state with the initial Bell state after decoding. Computationally, given a noise channel, given an encoding, you can find a decoding fairly efficiently. Conversely, given a decoding and a noise channel, you can find an encoding efficiently. And what Kishore was talking about seesaw was that people can do this kind of sequentially to converge on some kind of optimal decoding. There's no guarantee you will converge, but yeah, so you can add more constraints to this kind of program. So each one of these steps is called a semi-definite program. If you can phrase some constraints that you want as those of a semi-definite program, or maybe more general, then yeah, it would be worth checking. I can say that we imposed a constraint for continuous variable codes on the energy of a code, on the average energy of a code. So for continuous variable spaces, it's important to kind of keep as much states as possible in the physical Hilbert space.
Yeah, I think I've seen like with Shubham, right?
No, this is with Kyungju, like way before. You can, well, maybe yeah, Shubham did this too. Yeah, he's aware of it. But you can a constraint you can add is imposing some expectation value of some observable to be less than or equal to some number. That's one constraint that you can add that I know about.
I mean, I'm asking because at some point with Andrew, we and some other people in the audience, we extended these things to approximate dynamical codes. So like, I mean, you use this quantum comp framework and so on, and because each of the operation is a CPTP map, you can try to like optimize for that. But let's say if I want a tensor structure within that, like, I mean, so I want some fixed number of gauge qubits and so on, and so we could make a jump from, let's say, subspace to this one. But I think I was like, I don't know if there is something in the middle that anybody has thought of, like at the subsystem level.
No, it sounds like a useful thing to check. I'm not aware. So going back to the basics again, in the Shannon theory that I mentioned, the minimal program that you want your error correcting code to satisfy is to yield a smaller probability of corruption than the unencoded probability of corruption. Because otherwise you could just send the information unencoded, and you don't need to suffer all this overhead that I mentioned. And this is what people typically focus on. In classical theory, they just improve this, decrease this probability. In quantum, because quantum systems are so fragile, because you're going to have to do gates on these things. What people really look for is something more ambitious. They find families of codes that have what's called a threshold. So this is a noise rate below which it should be possible to construct, for which there exists an error correcting code that can protect arbitrarily well. And we can quantify that by this thing called the gain, just a ratio of the two probabilities. And if they're the same, then you're not doing anything with your error correction that's helpful. That's called break-even QEC. Naively, if you were to implement this in an experiment that's not super precise, you're actually going to do worse, most likely, with your overhead. So there were some experiments these past 10 years looking at, whether they can even reach break-even, so that they can at least show that all this overhead and acrobatics with this error correction actually is helpful. Of course, you want to go beyond break even. So this break even QEC is called a pseudo threshold sometimes. And you want to go, of course, beyond break even. But then the idea of a threshold is that now you have a family of codes for increasing numbers of qubits or whatever bodies, subsystems you have, oscillators, modes, etc. You have some number n of them, and you're taking that number to infinity, and the gain will keep growing with each element of the family for any probability of physical corruption that's below the threshold. And if it's above the threshold, it'll actually keep decreasing, and so it'll approach 0. So in the limit of n going to infinity, you're going to have this kind of stepwise thing that your fidelity will be perfect up to the threshold, and then you're going to completely die off. So the threshold is often only defined for a single noise channel. So it's, there's a lot of calculations that look at calculating thresholds for particular noise channels. Those noise channels are often just kind of like your usual Pauli channels and not actual physical, what happens in the actual physical reality. So you have to be careful about that. They exist for storage or computation. So you can actually use them for, you can actually calculate what is the threshold of doing some gate. Not only storing the information, but also implementing a gate on top of it. And the two kinds of thresholds that kind of I'm aware of, you can derive a threshold of using a concatenated family, which means you just keep encoding in the same family over and over again. You encode the physical qubits, you encode physical qubits in some logical, and then you take blocks of that and you encode the logicals again, use them as physicals to encode another layer of logical. So the physicals and logicals kind of have to match up so you can connect them, but you could do this with, say, for example, the Steen code, which was one of the first thresholds. And if you keep doing this, you actually get a threshold suppression of noise rate that's beneficial relative to the overhead you have to do this. Another set of thresholds deals with QLDPC codes. So there you include your topological codes, where the threshold there is actually connected to statistical mechanical models and phase transitions between them. So this threshold is really like a thermodynamic quantity that you want to think of as existing explicitly only in the n equal to infinity limit. And if the code that you're studying underlies or is related to some phase of matter, then that quantity actually becomes related to some kind of thermodynamic quantity of the associated phase. It would be interesting to study thresholds of QLDPC codes a little bit more. Some of them, because they have linear distance, like they're asymptotically good, they're basically guaranteed to have a threshold. It's not as clear what that threshold is related to, if it's related to some kind of phase of matter or not on a non-geometrically local geometry. There's kind of an active effort studying that right now. Okay, so now types of noise. This is something I should have studied in the beginning, but since we have some now experience under our belt, I can introduce more complicated noise and then give you a kind of a more bigger overall context. So I've arranged this kind of loosely at using these two axes. On the vertical axis is Pauli and non-Pauli. On the horizontal is whether you're easy to correct or hard to correct, meaning that few codes can actually correct it. So very conventional kind of noise models, toy models, are these kinds of examples of Pauli channels where each Krauss operator is a Pauli. Here, independent X Z noise is just a combination of channels that one implements an X flip on each qubit with probability P1, and one implements a Z on each qubit with probability P2. Those respective channels have another Krauss operator that's the identity with probability 1 minus P1, 1 minus P2 respectively. And you just act with those on every qubit, combine those, and you get this independent XZ channel characterized by two probabilities. Another channel is this depolarizing channel, which applies bit phase and bit phase at the same probability. So it's got 4 crosses, identity, and then these 3 errors with probability P on each qubit. Some more erasure-related channels are biased erasure and erasure, where erasure is basically you have a flag which tells you, this subsystem has completely basically disappeared. This factor in your n qubit and subsystem space. So like one of the qubits has been erased. So it's mapped to like a state E, which means it's completely kind of been decoherent. And you know which one that is. Biased erasure is kind of a similar channel, but it's a bit easier to handle. And amplitude damping is not erasure, so it shouldn't be really in this set of channels, but it's also not super difficult. But it's the first channel that I want to flag that's not containing an identity Krauss operator. So there's no probability of no amplitude damping error whatsoever. Amplitude damping is something that maps you from 1 to 0. It's basically collapsing you to the 0 state. It's modeling loss of excitations, leakage of energy out of your system. And with those kinds of channels, there is no identity Krauss operator because as time progresses, you have to kind of re-update what your expectation is of the state. And that in itself is a Krauss operator. So basically, this kind of amplitude damping has jumps that happen suddenly from 1 to 0, excitations like emission. And there's another compensating Krauss operator that's not identity that basically tells you, well, if you don't have emission happening after a while, that means you probably never had anything in the 1 state to begin with. So it reweighs your probabilities of states to be closer to the 0 state when you don't have any, which basically suggests that you never had anything in the 1 state. Some harder non-Pauli channels are these. So deletion is basically unknown erasure. And so for that, permutation and variant codes are very useful because there it doesn't matter which part you erased because everything is the same. They're permutationally symmetric. So there deletion is equal to erasure, but otherwise deletion is more difficult than erasure because you didn't know which qubit got erased. One of the most difficult kinds of noise that we encountered is actually a transition type of error. So this happens in atomic molecular environments where you have an environment that's very sensitive to which energy state has relaxed down to which other energy state. So the relaxation processes are all distinguishable. And then if they are, then you have this kind of transition. So for example, for oscillators, you have these Fock states, and if you lose a photon, the transition energies are all the same in the Fock states, and so you don't distinguish between which state you started with. But in a molecular environment or atomic environment, you can. And this becomes a problem because essentially, if you have an error that's this kind of like outer product, a single outer product between some states, phi and psi, it means that you cannot use psi to construct a code at all because it's just impossible to correct this kind of error. Another type of noise that people study that's very difficult is noise that has correlations in time or space. Correlated here means correlations in space. So you have some noise that's, is correlated with some other Pauli far-ish away. If it's far, then it's not only correlated, it's also non-local, which is tricky. But this is something that you really have to study if you're building a device, because this can happen. Your gadgets, your chips may have these kinds of errors. If you're correlated in time, you're called non-Markovian, and that also can happen. Oh, example of correlated noise. A burst error, like a cosmic ray. It's correlated across your whole chip, and it just blasts your chip and kills everything.
Do we have any threshold theorem, let's say, for noise that is both correlated in space and time?
Ooh, and time. I'm not sure. I think there's some some theorems for space. Not sure about time.
Yeah, like
Have to check.
for example, in Gottman's book, like Daniel basically he mentioned that correlated noise can decrease it by orders of magnitude, but I'm not sure whether the book is up to date. So, like I was wondering whether we have threshold theorem for a spatiotemporal noise, because that's the real danger, right?
Right. Yeah, I remember updating the zoo. You want to check qubit code, I think, or qubit stabilizer code entries. There's some thresholds that have been developed on top of like these first papers. That's a good question. Speaking of thresholds, here's some examples of thresholds that happen for the toric code, so for the surface code on a torus. I've extracted these from here, so all the references are in there. With erasures, you can actually recover the information after half the qubits have been erased, which is pretty amazing. Rough, like on average. The amplitude damping also has a pretty high threshold, turns out. Independent X and Z and depolarizing have these thresholds. These are related to statistical mechanical models. This one was the first one, I think, that started this whole connection between statistical mechanics and thresholds. And this is true only if the probabilities are the same. If you have what's called the noise biased regime, then one of these probabilities is going to be a lot smaller than the others. I should say like maybe P1 much greater than P2 instead of P1 going to 1, because that's just that's different limit. So basically the probability you basically you're going to a limit where you're effectively you only need a classical code. So it's a little bit artificial to be like super deep in that limit, but it's interesting and important to look at that limit because as you crank up the relative noise relative to each other, you actually get very high thresholds. So here you can get something as high as 50%. Depolarizing noise also has this threshold, right? So that's kind of like a cross check of how well you can do against these kinds of noise errors, kinds of noise. All right, so now to wrap up, I'll have a few slides on fault tolerance. So this Shannon paradigm that I mentioned is not the full story. In the quantum world, in the classical world, it's not too bad because it turns out that classical gates really were pretty fault tolerant, classical digital gates. But in quantum, you're effectively doing or approximating a continuous, unitary evolution. So you're going to have to be a lot more precise because of that and because quantum systems are fragile. So you're not only dealing with more fragile systems, you're also dealing with continuous parameter family of gates that you're approximating or trying to implement. So in this case, you do have to worry about fault tolerance a lot more. And in this case, you basically will have errors occurring everywhere in the decoding and the encoding and the gates everywhere. And you have to make sure that those errors don't get amplified to errors that cannot be handled by your decoder. Moreover, you have to make sure that errors that happen in the decoder don't completely screw up your decoder in a way that, that'll screw up the code. So this necessarily, because a single shot of decoding is, difficult, is going to have errors in it. This it basically implies that you have to apply this decoder many times, and you have to collect all the measurements and look at them and compare them and see if there's any kind of temporal errors that have happened. And this is this kind of art that people do whenever they talk about the surface code. That you're not just decoding in space, you're also decoding in time. And for the surface code in particular, the structure of the time decoder is very similar to the structure of the spatial decoder. Anyway, I'm getting ahead of myself. I'm just recapping here the Shannon formalism. So just to reintroduce fault tolerance, you want to apply operations now, G, on the message that is embedded within this noisy environment. So it's encoded in the noise. And you want to apply this such that when you permute the G through the N, so here G is invertible, so you just apply G inverse G, just multiply by G inverse G from the right side of N. And then you define N tilde to be the N conjugated by G. So if you have this kind of noise happen, this kind of gate, you apply this gate here, then you move it through. You know how it acts, how the perfect gate acts in the encoded information. So here you basically said, okay, I have a perfect gate, but now you have a noise channel that has been conjugated by the gate. And the purpose of this is to make sure that this noise channel is still correctable by the decoder. Okay. So this conjugation by G, you want to design it so that it does not amplify errors that are in the noise, such that now the resulting noise channel will be uncorrectable. I want to flash this slide because this is a nice summary of one of the oldest and most commonly used formalisms to determine whether errors get amplified from correctable to non-correctable. And it's very natural because we already know that we have a metric on our errors. We have a notion of severity. We have this kind of Hamming type thing where up to the distance, everything's correctable. And after that, it's not. And the distance is measured in the weight, in the support of your pallies, right? So for these kinds of Hamming type metrics, it's very nice to come up with so-called filter formalism because we have a notion of weight. And so you can define, so basically you can project onto error spaces, the code space and error spaces that have a certain weight of that can be obtained from the code space by acting with errors up to a certain weight. And this projects onto spaces that only deal with errors up to a certain weight. And this kind of like cutting and projection can be used to see if you've amplified errors or not. So you can define what's called an R filter. This is a projection onto code space and error spaces up to and including weight R. So then what you can do is you can say, well, okay, let's assume we have a certain weight errors that have happened. So we're going to restrict to that, meaning we're going to project using this R filter from one side. And then let's say whatever your gadget is that you're projecting, your noisy gadget, we say we have incoming some errors up to weight R. That's implied by our projection from one side. And then we want to ensure that our gadget doesn't amplify the errors past some weight R plus S. So then we'll stick in a filter from the other side that, cuts out anything that's past weight at R plus S. And that's the basic fundamental property of this propagation column. So here, every row is just some gadget, okay? And every column is so the column here that I'm talking about is this propagation property. And when you sandwich this gadget with the two filters, they better be the same as if you just applied one filter. That's the whole property, okay? So here you have a gate, circle is a gate, and you have some errors coming in R, and this gate is going to do something to these errors, going to propagate them. And we want to make sure that it doesn't propagate them past R plus S weight. So we say, okay, well then that means this has to be equal to this doubly sandwiched thing. And S and R have to be such that they're less than the number of correctable errors in the code. So then the distance over 2, which is T here, it's defined to be T. So I want to make sure that you're not scared off by this because it's a very simple idea. It's just applied very digitally and painstakingly to all the different gadgets. Okay, That's the propagation property. And the correctness property merely just makes sure that the gate does what it needs to do. Like these gadgets, actually, these are encoded gadgets. And you want to make sure that whatever they do on the code, forget errors, just whatever they do on the encoded information better be the same as what you actually do on the unencoded information using the same kind of gate. So this red things are just things that you apply on the unencoded information, and the encoded information better be the same. So if you apply it while you're encoded, it better be the same as first applying it on the unencoded information and then encoding. So those are basically the main two properties of the extract formalism: for correctness and whether the gadget propagates errors or not. So that's just a summary. I think it's good to have this picture around. Sorry, I've forgotten to erase the QIP talks here that are about this, but there's a lot of action in fault tolerance right now because people do want to do operations. We can't just do memories. And I'll just flash this slide that talks about a little of the basics of fault tolerance. One of the key areas of fault tolerance is the error correction itself. When you measure errors, so when you detect syndromes, those circuits will have noise. So you may not detect the right syndrome. Say you had an error happen on the 5th qubit, and there's a syndrome corresponding to that. Well, you do a measurement of the syndrome, you get a measurement error, let's say, on one of your syndrome bits, and then you get the wrong syndrome, and you weren't actually there. And so the recovery you pick will not be the same one that you need, and it may recover information in a wrong way, and you'll have an error remaining that may be different because you've now caused the error to change based on your recovery, using the wrong recovery. So what's important to design if you're building a quantum computer is a syndrome extraction circuit that is fault tolerant to certain errors that your code can handle. And one of the things that you want to make sure is that whatever errors your syndrome gadget does, which is this C0 kind of gadget, they don't carry over back to your physical qubits. So let's say you have some error here, and the C0 gate, if it's a Z error, the C0 gate may propagate it, and because of if you permute a C0 gate, a Z error through a C0 gate, we'll get a Z error on this side, and now because you have two C0 gates, you have two Z errors that have occurred from the Z error acting on the two physical qubits. These are called hook errors, and they are so-called backpropagate to the physical qubits. And you want to make sure to avoid them, and there's different tricks to avoiding them. One is to try to detect them using ancillas to your ancillas, which are called flags. So you attach extra qubits that you use solely for detecting different kinds of ancilla errors that are not detectable by your measurement. I want to mention data syndrome codes, actually, where the check measurements, the syndrome extraction itself, the syndrome measurements, the syndromes themselves are encoded in an error correcting code, a classical code. And so that if you have errors in the syndrome measurements, you can actually look at all the syndromes and figure out how to correct that error because there's redundancy within the syndrome space itself. So in the CS community, that's called data syndrome codes. But in the CSS community, you actually you can encode this redundancy in another chain complex, like by adding an extra layer to your chain. So another thing that's very simple that can actually avoid hook errors is just actually ordering your C0 gates in a particular way. Turns out that if you just pick, so a syndrome extraction of, say, like these 4 qubits, 0, 1, 2, 0, 1, 3, 4 in the surface code, extracting this check that's on the square, just applies C0 gates to these 4 qubits in some sequence and then measures. Well, if you merely change the order of the C0 gates, it turns out you can avoid hook errors. And this was noticed by this paper. Right, so there's lots of different strategies to mitigate this. Just define another distance. It's called the circuit level distance or the effective distance. It's the minimum number of faulty operations during syndrome measurement that's required to make an undetectable error. So this distance is basically kind of quantifying your hook errors, and it's less than or equal to the actual code distance. That's more of a space-time quantity, basically, that's relevant to syndrome extraction. And you want to basically get it as high as possible, and you call it code distance preserving if it admits syndrome extraction circuits with this distance. Now, I reemphasize this is an art, because given a code with parameters n, k, and d, I personally, and nobody I've talked to, has any idea of whether that code will have distance preserving properties or syndrome extraction circuits that approach, whose circuit level distance approaches the distance. So there's, I think, something kind of a hole here between or gap between the parameters of the code, structure of the code, and whether or not it admits nice, robust, fault-tolerant syndrome extraction circuits. And I can't quite understand if that gap can be filled or not. And just another jargon, some piece of jargon, the single shot code is something where if you keep doing syndrome extractions, you'll have errors everywhere, but the errors are going to be small, and your syndrome extraction is going to correct more errors than the new errors that will occur, and so things will be bounded, both syndrome and data errors, physical qubit errors, and the syndrome errors will be bounded. Those are called single shot codes. All right, I think maybe one more slide. There is a very general paper by, well, a conjecture, a very general conjecture.
Can you go to the previous slide? So basically you're saying that, I mean, okay, so the notion distance preserving thing, right? So normally we talk about, like n and k, and basically they are very much, like spatial object. And even the distance that we talk about, that's also spatial motion, like, qubits in space, and there are errors there, and you want to look for robustness. But what you are saying is that what if someone is interested in, this spatio-temporal distance, because when we are talking about fault tolerance, it's a spatio-temporal quantity, and taking into account all the measurement errors and everything together, we should be talking about distance for a maybe fault tolerance protocol, or I don't know, like, I mean, that's what you are hinting, like maybe like some notion of like tolerance against noise, not for the code, but at the level of fault tolerance.
Well, that's what these types of distances are measuring, yes. So yeah, so you can phrase it that way. And this kind of temporal piece is something that doesn't seem to be present in the actual spatial characteristics of the code, namely n, k, and d. It's kind of an extra layer you have to worry about. At least in the chain complexes, it's kind of an extra layer. I think this is an active study. I mean, like there's these space-time codes that try to map codes between, like Wick rotate between space and time, and then you guys have this kind of general conditions on these super channels. I personally don't have a clear, crisp understanding of the relationship between the space and these kind of fault-tolerant quantities. Yeah, so this is a very active area, okay? That's what I guess the take home is. So learn error correction, and then if you want to, be at the forefront, study fault tolerance as well. Yeah, so there's a very general conjecture about fault tolerance that basically says that any kind of fault tolerant gate you can reformulate, recast as a topological Berry phase or Berry matrix on some kind of adiabatically deformed path of your states in your code. So a Berry phase is something you get by deforming in a closed paths in some loop, a continuous parameter family of states. Berry matrix is something you get when you do it with a subspace. Overall, Berry matrix is really just an informal name of a holonomy. And this holonomy can come from, will depend on the path, of course, but it can depend on the path in very special ways. So if it depends on the geometry of the path, namely that if small changes in the path change the end effect, then that's not a topological Berry matrix. That's not a topological holonomy. And that corresponds to a non-fault tolerant gate. But if the Berry matrix depends only on the topology of the path, meaning how many holes have been, circled by the path and what kind of loop this is in terms of homotopy class, then, and if it only depends on that, then it's called a topological Berry phase or a monodromy, because monodromies are basically changes of like coordinates that you have to do to re-parameterize your end point to be the same parameters as the point you started at, like going from 0 to 2 pi and then mapping 2 pi back to 0 because 0 and 2 pi are identified. And there's a conjecture that any fault tolerant gate can be rephrased as this kind of some kind of a closed loop path in some continuous parameter space where the holonomy only depends on the topological features of the parameter space. Okay, that's the conjecture. And this was put forth by Gottesman and Zhang and worked out for like the 5-qubit code and the toric code. So the hard part here is like figuring out, well, we have fault tolerant gates, everything's discrete, and you have to embed these things in some continuous parameter family, some continuous parameter space in a sensible way. This paper deals with that. In parallel, so right, and you should already kind of smell something similar in the topological code slides, where I mentioned, well, that a lot of these kinds of fault tolerant gates that people do are these mapping class group elements on your geometry, and those also correspond to non-contractible loops, but just in like the geometry of the qubits. They're discrete because you kind of move the qubits around in a discretized fashion, but nevertheless, it does feel similar. Not continuous, so there's some work to be done, but it feels very much the same. This kind of monodromy was explicitly determined for GKP codes, which are these lattice codes. So there, everything is continuous. So, it's a natural way to try to verify this conjecture, and it was indeed verified. You can parameterize the space of all lattices in continuous fashion. And I want to mention 2 other cases of this. In parallel, in the condensed matter community, the way they study different kinds of braiding and of different topological phases, like these quantum Hall wave functions, is exactly in terms of monodromy. So there, the gates are already worked out as a monodromy right from the start. And this kind of work does very similar math as this kind of work, but it was done, basically this kind of stuff is done independently. So it's very interesting to connect the 2 communities. And I want to shamelessly advertise that we found similar behavior in molecules, in rotational states of molecules. So now you're not in a many-body state, you're just in a single molecule orientation, but the space of orientations is quite exotic. It has topological properties, so that if you go in a closed loop in the space of orientations, you actually get a monodromy as well. And this is true for all molecules, all rigid molecules, because we classified that here. So this keeps popping up, and I thought it was very interesting to flash because maybe somebody can prove this more generally.
So is this like, okay, so is it like some instances that people have seen, or like, or in these instances at least there is some necessary, like, or sufficient condition that people have shown that, let's say I work with qubit stabilizer codes, then the fault tolerant gates, they will they will like both necessary and sufficient, like this monodromy is both necessary as well as sufficient for fault tolerance of the logical gates for, let's say, this qubit stabilizer code, for example.
Right. I don't know if it's sufficient. I don't know if it's necessary. Well, sorry. If you're a fault tolerant gate, then you should be rephrasable as a monodromy. So I don't know if you can realize all monodromies as fault tolerant gates. But yeah, I mean that's basically what this paper studies. They embed your code and the gates and the noise in some continuous kind of parameter space so that you can do continuous evolution. You do these monodromies there. And these two place spaces, these are continuous variable spaces from the start, so everything's already continuous from the start. And here, that's also the same. Everything is continuous. These Z's, these W's are continuous variables. So here, things are discrete. So here, you have to kind of redo what these guys did. And that's not been fully done. How much time do I have? This is, I think, maybe the last
10
slide.
minutes.
About
15
10
good.
minutes.
Yeah.
Good, yeah. So so just to wrap up, I kind of want to tell you that QEC is really, the reason it's exciting to me is really because it makes a lot of connections. It's not just that it's exciting because it's required to build a quantum computer, but to me, it connects many different fields. So I just want to list kind of the main thrusts of the field. Kind of on more on the, so it's been splitting recently, I think, in a kind of a theory and applied QEC. So, you know, this first point is more of like a theory topic where you're just kind of cooking up what's possible. So these asymptotically good QLDPC codes, you know, they're not super practical, but it was important to figure out that it's possible because now we know we have something to shoot for. These singleton bound approaching approximate codes are also something that's not super practical, but important to know about. There's all sorts of different abstract topics. This is that people study and determine whether there exist codes for it. Very much to computer science because a lot of these types of codes are related to very deep issues in computer science. On the other hand, QEC is also practical because, you know, a lot of companies want to study the surface code because they want to implement it in their devices. And so there's lots of codes that are now instead more tailored to practical use cases where you know, in this case, you want to worry more about the device than the theory because the device will kind of dictate what the noise is and will tell you what kind of code is best compatible with that device. Right, so I guess these points 2 and 3 are very similar. I guess what I meant to say that point 3 is really where you're working specifically with devices to directly realize codes. And these codes may not be codes that people have built before. They may be codes that are kind of adapted from existing codes to tailor to the device. While in point 2, you kind of study codes that are naturally like geometrically local and have some kind of fault tolerance properties, but are not necessarily dictated by some device. Sorry, yeah. So those are slightly different cases. So, for example, people who study phases of matter that are occurring in 2 and 3D, you know, are indirectly helping study codes that may be later useful for some device. And on that note, you know, if you go deeper into the phases of matter and you start to connect properties of quantum matter to the error correcting codes, there's a lot more where that came from, not just topological order, which is probably the most useful for protection, but there's also Fracton order, eigenstate thermalization hypothesis, matrix product state, phases that can be expressed in terms of matrix product states in like even 1D, where it's interesting to look at low energy states that have some kind of intrinsic protection that stems from the properties of the phase. In another high energy area of physics, people I mentioned have these kinds of stabilizer code encoders, which are tiled in a hyperbolic fashion, which actually mimics this kind of ADS-CFT correspondence in holographic physics. There are a few other codes that, namely, I think Brian Swingle group was doing this code here, where you have some kind of field theories from high energy physics that people study, not just the holographic ones, which actually have some error correction built in. I find that very interesting. Not super practical, but again, just a proof of principle. It's kind of interesting to study. And I didn't mention this much, but you know, in quantum sensing, you know, LIGO and other cases, there's noise as well. And one way to mitigate that, or one way to try to get rid of the noise, is to encode it in an error correcting code. However, now you have competition, so you want to protect against noise, but you don't want to kill off your signal. So now you have to kind of worry about, okay, what's the noise, what's the signal? And there's a lot of kind of a busy area for that, is this error-corrected sensing, error-corrected metrology. So that's kind of a QEC in a nutshell. I have updated this slide. I want to acknowledge Philippe, who's dutifully been writing 10,000 lines of code for the website and been amazing to collaborate with him. We currently have just over 1,000 codes. We continuously add them, although I have to say recently, past 8 months, I've been running behind. The QEC field is really, I've noticed, exploded. There's a handful of papers a day now, and so it's very difficult to keep track of this. But we do hope to try to sustain the zoo in some way. I've had consultations, so these people do respond to emails, basically. This is why they're here. They've helped consult, how to organize the zoo best. I've taught a course along with Michael Golans, and then Mike Vasmir taught a course in Waterloo or Perimeter, where we've all assigned zoo entries for homework. This spearheaded the entire zoo from the beginning, so I want to thank all those students for helping out kickstart this project. Nat has been very helpful in helping me understand condensed matter. And we have a QEC Discord, so scan this QR code if you want to join. It's relatively active. There's job postings there and some discussions as well. So I think that wraps it up, and I want to thank you for giving me 6 hours of your time and for making it all the way this way, all the way to the end here. And thanks Atul and Kishore for this opportunity to give this talk again. Thanks.